Okay, great. So, hi everybody. As you can see, and as you've been told, yeah, I'm James. I'm a PhD student in statistics at the University of Warwick in England. I only started in like last October, so I'm quite new. But yeah, I've been coming to the reading group for like the last 2, 3 months. I haven't been able to go every week, but whenever I've been able to come, I've been coming, and and that's been great. And I really wanted to present this this paper. So it's not my paper. I'm not an expert on this, but I thought it was really cool, and it's trying to kind of bring a more of a like a statistical kind of perspective to some of this evaluation work. So yeah, I'm still like fairly new to evals. And I'm hoping in the discussion at the end, I'm kind of hoping we could have more of like a like informal discussion rather than it being too much of a Q&A. And yeah, I'm hoping I can learn lots from everybody else too, and we can all kind of learn from each other because I'm kind of proposing or suggesting that this is like a valuable thing to be learning, to be considering. But it's not necessarily like a solution to everything. It's more of a nice framework that we can use to hopefully kind of make evaluations more formal, more rigorous, and make them better, and make it better for AI safety. You'll see I've got I've got 32 slides, which might seem like quite a lot, but I assure you that in the middle, several are like one line. We got some images because I thought everybody needs a break in the middle because some of the stats stuff is like it's not too bad, but it can seem a bit like dense. Um, and we're going to take quite like a theoretical focus. So if you want to afterwards, there's some really cool like plots and stuff in the paper, and you can go and look at that. But I think so, like often when you're looking at a paper like this, it's the results section that's like really informative. Here, surprisingly enough, it's actually not so much like that. Most of the results are basically what you'd expect from from lots of the theory. Um, and we're going to kind of take that kind of perspective, and hopefully that will all be good. So if anybody's got, as Matt said, if anybody's got any questions, just feel free to like interrupt me or put your virtual hand thing up, and I'll get to you. Um, and also, if anybody else knows the answer to anybody's questions, also again, feel free to like to jump in because yeah, let's make it as kind of informal as we can in that sense. Um, okay, so. Yeah, I'm planning to make it like 35 minutes. And if I talk any more on the first slide, it's not going to be 35 minutes. So let's go. So yeah, the paper's scaling up active testing to LLMs. It's got 6 authors. They're from Oxford, Computer Science and Stats. And Tom Rainforth gets his own line, not intentionally, but I think he deserves it. He's quite young, but he's quite a big name. Um, in this area of statistics called Bayesian experimental design, which yeah, his kind of group called RAIN-ML, they made some big breakthroughs in the early like 2020s. He went from like Bayesian experimental design, it's called BED, which is a lot easier to say than Bayesian experimental design, so I'll say that. But yeah, BED was like this nice formal framework for experimental design for like intelligent data acquisition. Um, if we're running an experiment, how can we choose what questions to ask, or what things to test? How can we choose that in the best way? And there was this really nice this framework called BED, but it was like completely impossible to use because it was like computationally just intractable. The maths was, you had these big integrals and you couldn't actually use it. So they took things from like deep learning, and they used deep learning for function approximation, and they managed to make it a really viable approach to experimental design. So he did lots of work on that, but he's now kind of moved into like LLM evals. So he's kind of falling under the AI safety umbrella. And if anybody's interested, if people are interested in what I talk about in the rest of this, um, I'd recommend there's a really cool like UCL stats seminar last October. If you type in Tom Rainforth's name, it comes up straight away, and it's getting LLMs to play 20 questions. And I thought it was really fun. So I'd recommend going and looking at that. But for now, I'll focus on this paper. And I just put here it was accepted in Europe's last year just to make it clear that like it's not a preprint. It's something that's kind of been accepted as a influential piece of like influential contribution to this area of research. So you can read the bullets as well as I can, but effectively, in terms of the core question we're asking here, if we're trying to evaluate, especially like frontier models, um, we should be very clear that, like, say we're considering GPT 4.5, not that that can really be used anymore, but anyway, say we're using considering GPT 4.5, rather than it being a single model, it might be better considered like a family of models because you can think of varying parameters like your temperature, your top P. I'm sure you can think of better ones than that. Um, you could have a temperature of zero point 0.9, you could have a temperature of 1.05. Um, so in some ways, and you might want to evaluate the model at these different temperatures or with different system prompts. So in some ways, it might be better to consider a model as a family of models. And as soon as you kind of think about things in those terms, and we consider in the next few years how many models are going to flood the market, and highly capable ones too, it's kind of hard to deny that however good your evaluation process is, it would be good to be able to do labeling efficiently. And when we talk about labeling, um, we basically mean like if we've got an input, which in the case of LLMs is normally going to be your prompt, and we're looking at like the label is some kind of notion of a ground truth. Now, this opens up all of these like philosophical boxes that we don't really want to get into right now, although it would be good in the discussion. But we're basically saying we've got an input and we've got this kind of ideal output, and that's our label. How we get the label, we don't need to worry about too much right now. Um, but we're using this label it allows us to compare how good the target model is at predicting, because we've kind of got this ground truth to calibrate things. And in terms of a solution, so we had this question, how do we evaluate frontier models efficiently given this kind of limited labeling budget? Oh, yes. See a hand.
Yeah, so that's just me. Yeah, so
Yeah.
just trying to motivate that first slide. And I know you have a lot of them that you get
Mhm.
through, but so like in some cases, it's like fairly simple. Just gonna add like to get like a label for a question, right? It's sometimes like we source like evals from like existing multiple choice questions or something like that. So it's sort of pre-baked in some sense.
Mhm.
But in many of the tasks that we're asking LLMs to do or trying to evaluate them with respect to, increasingly, even establishing what that label is supposed to be is quite challenging. And there's like for instance, to say nothing about like how much effort is going into the construction of the prompt question, right? So like these are the situations where like there's just like it matters a lot, how which ones of those we are using because supposing they were all equally costly, you'd want to focus on the ones that to possibly like acquire, you would want to focus on the ones that are for some reason going to be the most informative among them all. Just a sort of clarifying sort of thing. And yeah, I mean, I guess I was just going to say that most people probably have confronted like evals or like benchmarks are like, simple like word problem, but the that kind of garden variety task is increasingly rare in terms of like importance in terms of evaluating LLMs. So yeah, that's where it might get more costly. Is like when like there's like very enormous like questions and a lot of output necessary in order uh, to find out what the answer is.
Yes.
Anyways,
Yeah.
just adding some color
No,
there.
it's a great, yeah. Yeah. Um, yeah. Okay. I'll keep going. So, and also with Eric, with your question, I thought we could come back to that at the end because, and for now, let's just assume that we don't want, um, like big evaluation costs because of, yeah, in terms of with what Matt was saying. Let's just say we kind of formalize things a bit later in the presentation, but let's just say we have this kind of fixed budget and we've got to stick to it. Um, yeah, okay. Let's keep going. So, in terms of a solution, active testing is a solution, and it's actually a very like general framework. So it's maybe not always best to say like we can't say this like um a magic solution that's going to solve all our problems. It doesn't solve everything, but um it's basically like a framework for doing intelligent data acquisition and choosing these labels efficiently. But we've kind of got like an inherent trade-off because we're trying to do this data acquisition, choose these labels in an efficient way in order to reduce cost. But at the same time, it's like in order to run these algorithms that help us do this data acquisition, that costs money. So if it costs too much to actually choose what things to label, then we're not improving on anything. And as soon as we're using LLMs, there are some kind of issues we run into, and we'll get onto those, which makes active testing much harder. And this paper kind of, as we'll see in the next slide, says this. The paper kind of identifies these three computational bottlenecks when we're trying to use active testing for LLM evals. And it proposed a solution to each of these bottlenecks. And in the words of the paper, shows that combining them makes active testing dramatically cheaper, which is quite the statement. Um, yeah, but before we get on to active testing, I'm sure some of you will have heard of active learning before. Um, and in some ways, you can think of active testing as basically the same as active learning. Actually, I Googled it and there's not very much that comes up for active testing and a ton comes up for active learning. But that's kind of why I like this paper because it was trying to, it's not saying we've got some revolutionary approach, but it's saying let's use some of the things we already know, some of the existing literature, and let's try and let's try and formalize certain things, do some sensible things, and hopefully things are going to work a bit better. So, in terms of active learning, that basically means instead of having like a fixed training set and just training a model, we're going to instead just start with, imagine we start with like a small training set with the potential to increase this in size, the potential to collect more data. Um, and then we use what's called an acquisition function. And if you know anything about like Bayesian optimization, it's a very like similar idea. Um, we use an acquisition function to tell us which inputs are best to label next. So the acquisition function basically takes as inputs um, like potential like inputs in the input space of the model, and then it like assigns a score to each of these inputs, saying how good it thinks it would be if we collected, um, you know, if we labeled that input. And yeah, as I put, we label, retrain, repeat. So um, we use acquisition function to get more inputs, sorry, to get more labels. We retrain the model. That gives us a new acquisition function, which tells us where's best to look now. Because if we keep looking in one area, we might start feeling quite confident about how the model is doing in that area. So then we want to go somewhere else. And we might be like going one at a time. So we could just go, let's maximize our acquisition function, like find the maximum, and then choose that point as what to label next. Or we could be in a setting where we want to do like 101 go. Like there's an example I came across where they were doing like testing these different chemical compounds on mice with some disease. I'm not sure what the disease was, but um, and it was like it was going to take, say, like the experiment was going to take 2 months. They were going to test how well the compound did for 2 months. Well, in this case, if you've got 12 mice, you can't just and in this case, the input would be the compound to try. Um, well, you can't just like do one at a time because you'd wait 2 months before you can get another one. We've got these 12 mice, so let's find the 12 points where the acquisition function gives us the best scores, um, and we'd use those. So, as I put, yeah, active testing very similar to active learning, but the key like conceptual difference is we're not training a model. We're trying to evaluate a model and choose labels that help us evaluate the model in the best way. And to be more kind of precise about this, we're trying to come up with a good estimate of the risk of a model, and we'll kind of formalize what we mean by risk in a few minutes. Um, Now, this slide might be slightly unnecessary, but I thought it was fun. Because obviously every week we're talking about model evaluation. And I found these three definitions. I literally just typed in what is model evaluation. The first one comes from Label Studio. I don't know what Label Studio do, unfortunately, but I thought it was very appropriate, given what we're talking about. And I'm sure you'll all agree that like these are good definitions, but they're also quite vague. Like, how well an AI system performs, or ensuring the models perform well or gauge the effectiveness are not particularly informative in terms of actually trying to formalize anything. So we're going to try and do this. Um, Now, before we do this, we're going to quickly go through a little bit of like estimation theory. Some people will like have seen all this before, some people won't have. So if anybody wants me to go into anything, we can. Otherwise, we'll go through it quite quickly. Um, and It was quite funny actually because my my search for a good textbook to kind of cover this, it took me to this like canonical reference called Casella and Berger, like canonical for statistical inference. It didn't actually have what I needed, but in the preface, it said the preface began by saying the best description of this book can be attributed to the California rock band The Grateful Dead. Um, and the words of their second album, "What a long, strange trip it's been." And I just wrote that down because I thought, with this section that's to come, I hope it's not too long nor too strange. But I hope that, although it's quite abstract, and I think that's quite useful in a way, we want to be careful to be very clear about what our framework's saying, what it gives us, and what it doesn't. And I've come up with some questions for the discussion at the end where we can kind of discuss this more. But for now, let's just like live in this world of a little bit of stats, a little bit of maths, and see where it takes us. So, introduction to estimation theory. We're going to assume that we've got some probability distribution. I haven't actually named it because that would just add even more notation to the mix. But we've got this probability distribution that depends on theta, and we're going to take a sample of size n. We've got n random variables, and then we're going to construct an estimator, which we're going to call theta hat. Hat just denotes we've got an estimator. Um, And yeah, this is just some function of our n random variables. And because it's a function of something random, it's also random itself. Um, and because it's random, we can think about its expectation and about its variance. And also something called bias. So bias is just the expectation of the difference between theta hat and theta. And just with some like of the standard properties of expectation, that just simplifies to expectation of theta hat minus theta. And now, if we've got an unbiased estimator, uh, you just imagine like the left-hand side is zero. So that's equivalent to saying the expectation of theta hat is equal to theta. So we're saying on average, like in reality, we can only get this estimator once. We take a sample, we construct the estimator once. But if it's unbiased, we're saying on average when we do this, if we could do this a million times and then take an average, we would get what we're trying to estimate. You know, dead on basically. Um, but obviously, being unbiased isn't necessarily like that useful because you could be unbiased, but 50% of the time you could be like 10 above what the estimate, uh, what we're trying to estimate. And 50% of the time we could be 10 below, and to this 10 could be like disastrous. Like we could be, it could be an absolute disaster if that is the case. So we'd prefer to think about variance. And that's what I got on this slide. So on with the bias, we have the expectation of theta hat minus theta. And here we've got the mean squared error, which is the expectation of the square of the square of the difference of theta hat minus theta. Um, and we'll get on briefly onto loss functions in a minute. But mean squared error is often like a commonly used loss function. It's not perfect, uh, but yeah, it's quite a good one to start with. But you'll see on this slide that it's closely related to the variance, especially when we've got a situation where our estimate is unbiased. So you can decompose the mean squared error into the variance plus the bias squared. The derivation for this is actually quite painful. So we're not going through that. And it's kind of besides the point. But what's kind of quite useful to notice on in the second bullet point is that if we're in this unbiased case, if we remember, if we go back, um, we had expectation of theta hat is equal to theta. So if we just put theta in place of expectation of theta hat, we just get the mean squared error. So here we've basically got this equivalence. In the unbiased case, we're trying to minimize our loss function. Our loss function is saying how good is our model doing, and it's basically about reducing the variance of our estimator. We've got this, some of you might have seen this a million times before, but it's just a nice little visualization of like low variance, low bias, high bias. And we kind of ideally want to be in this case, we're in the low bias and low variance. But there's like kind of an inherent trade-off between bias and variance. Um, so it's in practice quite difficult to achieve that, but we want to get as close to that as possible. Um, Again, I'm sure this is like very familiar to lots of people, but we'll just go over it briefly. So if you just got like flipping a coin n times and you get one for heads, zero for tails, a really good estimator is just the sample mean. So we just take the mean of that sample of n flips. And we can show that this is unbiased. And also the variance decreases nicely with n. So like, proportional to 1 over n. Um, and I've got a little like graph, which is just like a 1 over x graph. But it's just like nice to see that, to kind of get in your head that we can very quickly, as we increase the number of observations, with this estimator and with lots of estimators, of this kind, like increase the number of observations, and we're very quickly reducing our variance. But the whole key point, the key problem is we can't get these observations for free. We need to intelligently choose, what we're going to label, what we're going to sample. Um, so yeah, it's really important we do that well because by doing that, we can reduce our variance. So let's formalize evaluation. Um, F is our target model. So in what follows, F is going to be our target model. Target model is just the thing we're trying to evaluate. This nice curly L is our loss function. Um, and yeah, this is like giving us some notion of like closeness of distance between the predictions of our target model and this kind of ground truth. And then we have this P eval. This is like a probability distribution. And we're basically imagining we've got some reference system and it behaves according to some probability distribution. So we're kind of living in yeah, we can call it an oracle. We're kind of living in this like slightly idealized world where this ground truth exists. Now, in reality, maybe this isn't, we're making a generalizing assumption. But um, I found this image in a book, in an active learning book, and I thought it was a slightly depressing image. And my point is that I don't think we should be thinking about things in these terms. Yeah, the Oracle could be a human annotator. That might be as good as it gets for us. Um, but a human half slumped over his laptop with something that looks a bit like a briefcase on the ground isn't quite the world we want to be living in. The whole point of all of this is that by kind of abstracting away all the real world, we can have this framework where we can reason about things in a really nice way. So instead, we can consider the Oracle at Delphi, the Pythia. I thought it was quite fun because like this is used like Eleuther AI. They use this to name something, and it's like used for something in the Large Hadron Collider. Anyway, I thought it was quite topical, um, because we want to kind of like let's let's take away all of our kind of human constraints and just imagine we can live in this world where we've got an oracle. It can prophesize, come up with these really good predictions for the future, and it's like as good as we get, as good as we can get. Um, and I found this nice image of Delphi, and it looks a bit like a paradise. And I kind of thought this is a really good way of getting in your head the fact that we have this beautiful place we can go to get our labels. Um, but it's going to be quite the trek to get there. So we can't just go for free. Um, and when we're there, we're getting this ground truth, this perfect notion of what is good for the model to give us. But in practice, it's not going to be that easy. Now after that break, we've got to go back to the boring black text. It's actually very, very dark blue, but I'm not sure you can tell that. Anyway, uh, so yeah, in terms of the kind of background for this paper, um, we want to be constructing a good estimator, a good estimate of the expected predicted loss, and this is R here. So it's taking the expectation over this p-eval distribution, this kind of perfect distribution. Um, and this is joint over both the inputs and the outputs. So we're kind of imagining we've got like we're in like the real world or the whatever mythological Greek world, whatever we want to be in. Uh, and these inputs and outputs are kind of paired in some way, and they're kind of appearing in nature. And they appear with some frequency, and this is kind of our probability distribution. And we're basically taking this expectation over the loss. So this is like a loss function, L. And this is giving some notion of some like measure of distance between f of x, which is the output of our model at x, and y, which is like the label, the ground truth, what's paired with x. And in this setting, we've got we're gonna consider where we like a situation where we've got n unlabeled test inputs. We call this like dpool. Um, and yeah, as I kind of alluded to, formally, we're going to say that if we're getting an output y or like a label y, this is sampled from this conditional distribution, this p-eval of y given x. Um, but it's costly, and therefore we're going to say we can't label everything. That's the whole point. We're going to have m labels where m is some number less than n. In practice, it's going to be probably quite a lot smaller, but we don't need to worry about specifically what that would be. So we can have like this is the most like basic approach is we can just construct like a basic Monte Carlo estimator, where basically what we do is uh, we just use our we pick randomly um, pick like m inputs from our pool, and we just consider what's the difference between and we label each of these, and then we consider what's the difference between the label and the output the model's giving us. And we just take an average. And this is going to be unbiased. It's like very simple to show that, but in general, it could be quite high variance. And yeah, it's technically called the subsample empirical risk, but anyway. And what we want to do here is we've got this as kind of our baseline, but we want to try and improve our choices of what the M indices are. So yeah, we've got some label budget M, and we don't want to sample uniformly. Instead, we want to do this non-uniformly. And as soon as we start doing things non-uniformly, we don't have unbiasedness. Um, and that's like a really key point to be aware of. We don't have unbiasedness. Um, like basically because we're sampling with respect to some like distribution, as you'll see, that's not p-eval, and therefore the math doesn't work basically. Um, So instead, at each step m, so at each step, as at each time we update um, like our acquisition function, we choose an input x with probability proportional to our acquisition function, and this is a key point. So when we're doing stuff with any model, what we do is we construct a surrogate. And a surrogate is basically like an approximation of this model we're trying to evaluate. That's simpler, it's easier to evaluate, easier to get outputs out of, and we can try and optimize. We can optimize that, or we can use that model to give us an acquisition function, and then we optimize that acquisition function, and it tells us where to look next. So it's not gonna be perfect because it isn't the true model, but it's as close as we can kind of reliably get. And as you can see here, so if we go back a couple of slides. Here we've got R as expectation over P eval, and here we've got the expectation over pi m, where pi m is our surrogate. So we're basically saying, uh, we're taking like an average of the loss for some input x. We're taking an average, like what on average do we expect the loss to be when we put in this X to our model and we compare it to a label Y. But the best we can do, we don't know what p-eval is. P-eval is living in Delphi with the Oracle, and we don't know what it is. Um, but we can construct this surrogate. We construct it by um, by using the labels that we do have. So we won't go into this. I just wanted to quickly show it to you, just to make it clear that we have this estimator, and as I said, when we sample non-uniformly, like a naive like Monte Carlo estimator, where we just that take like a simple average that doesn't work for giving us unbiasedness. It's biased, but we can use this kind of clever like almost reweighting. You'll see the QMs. That's just like this is the if we go back a slide. Um, Here I said the probability is proportional to an acquisition function. This is basically just turning our scores, like our outputs from our acquisition function, into a probability distribution. It's like normalizing things. And this estimator is is unbiased. So we can use this, whatever our surrogate is, whatever our label, whatever labels we pick, it doesn't matter. The point is we can construct an estimator in a way that gives us unbiasedness. And then once you've got this, as we saw several slides ago, um, for all the Oracle stuff, uh, if we've got unbiasedness, the only thing we need to consider if we're trying to minimize our loss function is is reducing the variance. That's what we got. That's what we got to consider. Um, Now, in the kind of active testing literature, there's a third approach, and here we use a surrogate again. But we don't just use it to decide what points to label next. We also use it directly to construct the risk. So if you notice here, our sums over all the points in our pool, when before it was over, it was 1 to m. So this was just over all our labeled points. And now we're going over every point. But obviously we haven't labeled all these points. So like what do we do? It's maybe not completely obvious, but the solution is to use our surrogate for this. So here we're um we're taking our expectation over our surrogate, um, and we're basically saying what does our surrogate think is going to happen? Because the surrogate's got some idea of if you put in this input what the output's going to be, and it's saying on average what does the surrogate think is going to happen if we put an xi, and we're going to try all of these points in our pool, and say just basically ask the surrogate. So the surrogate isn't our oracle. It's like a if anybody's got a good analogy, tell me. I haven't thought of one. It's less good than the Oracle, but it's still like it's okay. Um, Maybe a bit more like that human slumped over the desk. Um, so yeah, as the bullet point says, risk is estimated. And I should say, I'm not sure if I said before, but when I say risk is just the expectation of the loss function. So it's just on average, what's the loss function going to be? Um, uh, yeah, so risk is estimated by simulating labels from the surrogate. And yeah. Yeah, it's not unbiased, because we haven't got this clever construction here. Um, but it can have very low variance because as we iterate, as we keep updating our surrogate model, we start to get closer and closer to the target model. We get a better and better approximation of the target model, and therefore our estimates are better and better. So in terms of what the paper contributes, um, it contributes, yeah, these three kind of main ways of improving things. Um, or at least, to be honest, the first two are kind of they're kind of using the same, they're doing the same thing to achieve these. But anyway, we'll discuss them separately. Um, so yeah, surrogate model training. Um, it can be very expensive to continually update the surrogate. So what we're going to do, we've got an LLM, and if we want a surrogate, we're basically saying we want some model that behaves like this LLM. But as you can imagine, it's going to be quite hard to have a model that's much kind of cheaper to use than an LLM without it being so kind of basic that it doesn't really do a good job of approximating what the LLM is. Um, you can't just use like a standard neural network because it's going to be nowhere near complex enough to be able to do this. But what they found, what Rainforth and his group, what they found was that you can take quite a cheap, like small language model, and you can use in-context learning where you just give it a few, um, samples like at the start of the prompt. On Here, I put a small amount of randomly acquired test data on some bits of data we've labeled, before we start. Um, we can use that and we can kind of hope, and it does kind of, it does well. We can hope that it takes this small language model slightly closer to our target model. And there's obviously many open questions here. What I'm discussing, I'm saying we want some surrogate that's a good approximation. How we do that, I had some questions at the end. I put like open questions, and I put that on there because there are many considerations here, and this paper is just, you know, like a first step towards improving how we do things. But in what they propose to do it like this, and then keep it fixed. So they're not even updating the surrogate. So normally, as you acquire more data, you keep updating the surrogate so it gets closer and closer to the target. Here we're just going to say we've got a surrogate at the start, we're just going to keep it fixed. And that's because updating the surrogate like is very expensive to do. We can't like get one more label and then update it like excitedly, like, oh, we got another label, let's like make the model better because it's very expensive obviously to to train language models. Um, uh, but as soon as we're doing this, we now can't really use the interpolation-based estimator because if we remember, when we're using that, we need the surrogate for constructing our estimator. And the whole benefit was that the surrogate was going to get quite good and then be a good way of constructing our estimator. Um, but here, if we're fixing at the start, it's not going to, we might start with 10 labels and eventually have 1,000 labels. Well, if we're using a surrogate that's just based on 10 labels for the entirety of the process, it's not going to be a very good match to the target. So we've got this trade-off between like, you know, the cost of updating a surrogate and the benefit that we have when our surrogate's close to our target. Because the better the surrogate is, the better you can kind of acquire data because you're kind of more aligned with what the reality of the target model is. Um, yeah, so instead of using this interpolation-based estimator, we use the sampling-based one. So we're still using this Lua estimator, and therefore it's still going to be unbiased. Um, And therefore, when we're trying to work out how to construct a good surrogate model, we're just thinking about variance reduction, and therefore like reducing the mean squared error. So yeah, I put here it's much less desirable to use interpolation-based active testing. So we don't want to do that. And in all the like empirical testing they did, they abandoned that way of doing things. So kind of a second point to make when we're keeping the surrogate fixed is that like throughout we're using the surrogate model to make predictions. So if we're doing interpolation-based active testing, which you've already said is undesirable, but in theory, somebody could come along and have a way of making this work. So we should consider it. Um, yeah, if we're doing interpolation-based testing, whenever we're constructing this estimate, the risk, that estimator we had, um, we're making predictions with the surrogate. And in both cases, we're making predictions whenever we compute the acquisition distribution. If we go back several slides, to here, um, yeah, whenever we do this, like our acquisitions, so our Qs come from our A's, and our A's here we're taking expectation over our pi m, our surrogate. So we're making predictions every time. Um, so although we're using a cheap language model, it's still not just like free to make tons of predictions. The whole point is we're making a lot of predictions because we've got to consider like every possible point we could label, and that's a lot of points. Um, so instead, we're fixing our surrogate, and then we don't have like pi one, pi two, pi three, pi four. We just have one fixed surrogate. We can we can you know compute how good a given label would be, um, or how likely different labels are to appear for every input in our pool, and then we're just done, and we can just keep all of those forever. And then as well as having to make predictions with the surrogate, there's something we haven't really touched on yet, which is the fact that we also have to make predictions with our target model. So we have to put a prompt into our like LLM and get an output. And obviously that's like fairly cheap to do, but it's not free. So whenever we've got in any of these expressions we've seen, whenever we've got f of x or f of xj or whatever, um, here, to do that, to have that, we've had to put in a prompt and into the LLM and get an output. And if we're using like considering like a frontier LLM, or say like a new LLM comes along that's like a huge model, it can be quite expensive to do this, especially if we're doing it a lot of times. We've got a big pool because we want a big pool, so we've got lots of options for where to label. But as soon as you have lots of options, we then have to evaluate each option one by one. So yeah, as I put, particularly expensive for large target models and large pool sets. Now, again, in the interpolation-based approach, giving you lots of reasons why this is a bad one. We can't really avoid that because it's used directly in the estimator that's constructed. So if we go back, we've got this f in here, so we can't avoid that. Um, but in the sampling-based approach, we can we can basically use this approximation where instead of having n target model predictions, we just have m, where m is some number that's like we already kind of said we want it to be like much less than n. And then this formula is a little bit the phi you don't need to worry too much about. It's basically taking like a probability distribution and turning it into a number we can compare with y. Um, it's just out of the paper, but here we're using the surrogate to like approximate the target model's predictions. Um, So instead of using the target to construct the acquisition function, we're instead using the surrogate. And obviously, if the surrogate's good, then this will work really well. As we've said, in practice, we're fixing it, so it's maybe not going to be as good as we'd want. And this is kind of an open question, and I'd be interested what people think about this. So yeah, in terms of open questions, um, active testing relies heavily on the surrogate being a good approximation of the target model. Um, I wonder if there are better approaches. It's actually interesting. The paper doesn't really have much of a discussion as to limitations. So I came up with these kind of myself. And it kind of makes sense why they did that because they were basically proposing a few ways of doing things better, and saying these are good steps forward. Um, and therefore there's not necessarily limitations because they're not making any kind of adopting any bold new ideas or anything like that. But yeah, the question is, are there better approaches than in-context learning? Could we use something like fine-tuning or a variant of this? Or is that always going to be too expensive? Like, could it ever be justified to do that? Um, and also, if we imagine like future LLMs being kind of conceptually different, would these approaches still work? What would be a good surrogate to use? Another point is that if labels are incorrect, so we can't all go and visit the Pythia. So if the labels are incorrect, things can fall apart really quickly because suddenly we're basing where we're looking, where we're labeling on previous labels of like that are informing our acquisition function, um, and things can fall apart really quickly. Because if you get a label that's wrong, but the label's telling us we're really far away from the ground truth, then our acquisition function is probably going to say, let's keep sampling here because the model's clearly doing badly. So let's keep seeing, um, it's useful to look at that to try and work out what our risk is. Um, But if that's incorrect, you can imagine that only if you only need might need a few of these labels that are slightly off, and suddenly the acquisition function is like sending all of our resources to an area that's actually doesn't need to be evaluated because we already kind of know it's doing well, but we thought it was doing badly. Um, and also, everybody should, if people are interested, yeah, looking at the paper, it basically confirms lots of things I've said in terms of these kind of intelligent ideas how to do things working quite well. But there's a big focus on classification tasks. And like this makes sense because here we can have some kind of ground truth. If we've got a question of like, if we've got like a maths question or just like a multiple choice kind of A, B, C, or D, and we say A is right and we're testing whether the LLM gets A or not, that's a situation where, we can very reliably say we do have this ground truth, it's perfect, and this framework works very nicely. But obviously, in practice, we often don't want to constrain ourselves to a situation where we're only looking at classification tasks. Um, and this brings up all sorts of kind of questions around yeah, the ground truth kind of notion that I discussed. Um, and yeah, a last thing to keep in mind is that active testing is it's cheaper. Like if we do it well, it's a way of making things more efficient, but it's not free. It's not just like a way of solving all our problems, but it's just a framework for how can we evaluate models in a more kind of principled, efficient way. So I'm basically done. I've got a few, this slide's got some like discussion questions. But if anybody else has got other things to discuss, we can discuss that. But these are some of the things I thought of. And yeah, thank you everybody for listening.